Algorithms for calculating variance play a major role in statistical computing. A key problem in the design of good algorithms for this problem is that formulas for the variance may involve sums of squares, which can lead to numerical instability as well as to arithmetic overflow when dealing with large values. Norvay algorithm, a formula for calculating the variance of an entire population of size n is a formula for calculating an unbiased estimate of the population variance from a finite sample of n observations is therefore a naive algorithm to calculate the estimated variance is given by the following. This algorithm can easily be adapted to compute the variance of a finite population, simply divide by n instead of NaA1 on the last line. Because some SQ and n can be very similar numbers, cancellation can lead to the precision of the result to be much less than the inherent precision of the floating point arithmetic used to perform the computation. Thus this algorithm should not be used in practice. This is particularly bad if the standard deviation is small relative to the mean. However, the algorithm can be improved by adopting the method of the assumed mean. Computing shifted data, we can use a property of the variance to avoid the catastrophic cancellation in this formula, namely the variance is invariant with respect to changes in a location parameter with any constant, which leads to the new formula. The closer is to the mean value the more accurate will be the result, but just choosing a value inside the sample's range will guarantee the desired stability. If the values are small then there are no problems with the sum of his squares. On the contrary, if they are large it necessarily means that the variance is large as well. In any case the second term in the formula is always smaller than the first one, therefore no cancellation may occur. If we take just the first sample as the algorithm can be written in Python programming language as this formula facilitate as well the incremental computation, that can be expressed as two-pass algorithm, an alternative approach, using a different formula for the variance. First computes the sample mean, and then computes the sum of the squares of the differences from the mean, where S is the standard deviation. This is given by the following pseudocode. This algorithm is always numerically stable, unless n is large. Although it can be worse if much of the data is very close to but not precisely equal to the mean and some are quite far away from it. The results of both of these simple algorithms can depend inordinately on the ordering of the data and can give poor results for very large datasets due to repeated round-off error in the accumulation of the sums. Techniques such as compensated summation can be used to combat this error to a degree. Compensated variant, the compensated summation version of the algorithm above reads. Online algorithm, incremental algorithm. It is often useful to be able to compute the variance in a single pass, inspecting each value only once. For example, when the data are being collected without enough storage to keep all the values, or when costs of memory access dominate those of computation. For such an online algorithm, a recurrence relation is required between quantities from which the required statistics can be calculated in a numerically stable fashion. The following formulas can be used to update the mean and variance of the sequence, for an additional element. Here, xn denotes the sample mean of the first n samples, s2n their sample variance, and I2 Namibian florins their population variance. It turns out that a more suitable quantity for updating is the sum of squares of differences from the mean, here denoted. A numerically stable algorithm is given below. It also computes the mean. This algorithm is due to Newth, who cites Welford, and it has been thoroughly analyzed. It is also common to denote AND. This algorithm is much less prone to loss of precision due to massive cancellation, but might not be as efficient because of the division operation inside the loop. For a particularly robust two-pass algorithm for computing the variance, first compute and subtract an estimate of the mean, and then use this algorithm on the residuals. The parallel algorithm below illustrates how to merge multiple sets of statistics calculated online. Decremental algorithm, according to incremental algorithm, removing a specific number out of the data set is performed by executing reverse form of incremental algorithm to calculate mean and variance of new data set. This function is used in calculating statistical information in a convolution operation. Here's the calculation. A compound algorithm for add or remove member to a data is given below. Weighted incremental algorithm. The algorithm can be extended to handle unequal sample weights, replacing the simple counter n with the sum of weights seen so far. West suggests this incremental algorithm. Parallel algorithm. Chan et al. Note that the above online algorithm 3 is a special case of an algorithm that works for any partition of the sample into sets. This may be useful when, for example, multiple processing units may be assigned to discrete parts of the input. Chan's method for estimating the mean is numerically unstable when and both are large, because the numerical error in is not scaled down in the way that it is in the case. In such cases, prefer. Example, assume that all floating point operations use the standard IEEE 754 double precision arithmetic. Consider the sample from an infinite population. Based on this sample, the estimated population mean is 10. And the unbiased estimate of population variance is 30. Both algorithm I and algorithm do compute these values correctly. Next, consider the sample, which gives rise to the same estimated variance as the first sample. Algorithm do computes this variance estimate correctly, but algorithm I returns 29.3333333333333332 instead of 30. While this loss of precision may be tolerable and viewed as a minor flaw of algorithm I, it is easy to find data that reveal a major flaw in the naive algorithm. Take the sample to be. Again, the estimated population variance of 30 is computed correctly by algorithm 2, but the naive algorithm now computes it as a 176.6666666666666666. This is a serious problem with algorithm I and is due to catastrophic cancellation in the subtraction of two similar numbers at the final stage of the algorithm. Higher-order statistics. Teribery extends Chan's formulae to calculating the third and fourth central moments, needed for example when estimating skewness and kurtosis. Here they are again the sums of powers of differences from the mean, giving skewness, kurtosis. For the incremental case, this simplifies to. By preserving the value, only one division operation is needed and the higher-order statistics can thus be calculated for little incremental cost. An example of the online algorithm for kurtosis implemented as described is. Par Copyright Bay further extends these results to arbitrary order central moments, for the incremental and the pairwise cases. One can also find their similar formulas for covariance. Choi and Sweetman offer two alternative methods to compute the skewness and kurtosis, each of which can save substantial computer memory requirements and CPU time in certain applications. The first approach is to compute the statistical moments by separating the data into bins and then computing the moments from the geometry of the resulting histogram, which effectively becomes a one-pass algorithm for higher moments. One benefit is that the statistical moment calculations can be carried out to arbitrary accuracy such that the computations can be tuned to the precision of, for example, the data storage format or the original measurement hardware. A relative histogram of a random variable can be constructed in the conventional way. The range of potential values is divided into bins and the number of occurrences within each bin are counted and plotted such that the area of each rectangle equals the portion of the sample values within that bin. Where and represent the frequency and the relative frequency at bin and is the total area of the histogram. After this normalization, the raw moments and central moments of can be calculated from the relative histogram. Where the superscript indicates the moments are calculated from the histogram. For constant bin width, these two expressions can be simplified using. The second approach from Choi and Sweetman is an analytical methodology to combine statistical moments from individual segments of a time history such that the resulting overall moments are those of the complete time history. This methodology could be used for parallel computation of statistical moments with subsequent combination of those moments, or for combination of statistical moments computed at sequential times. If sets of statistical moments are known, then each can be expressed in terms of the equivalent raw moments. Where is generally taken to be the duration of the time history, or the number of points if is constant. The benefit of expressing the statistical moments in terms of is that the sets can be combined by addition, and there is no upper limit on the value of where the subscript represents the concatenated time history or combined. These combined values of can then be inversely transformed into raw moments representing the complete concatenated time history. Known relationships between the raw moments and the central moments are then used to compute the central moments of the concatenated time history. Finally, the statistical moments of the concatenated history are computed from the central moments. Covariance. Very similar algorithms can be used to compute the covariance. The naive algorithm is. For the algorithm above, one could use the following pseudocode. As for the variance, the covariance of two random variables is also shift invariant, so given that and are whatever two constant values it can be written. And again choosing a value inside the range of values will stabilize the formula against catastrophic cancellation as well as make it more robust against big sums. Taking the first value of each dataset, the algorithm can be written as. The two-pass algorithm first computes the sample means, and then the covariance. The two-pass algorithm may be written as. A slightly more accurate compensated version performs the full naive algorithm on the residuals. The final sumsum should be 0, but the second pass compensates for any small error. A stable one-pass algorithm exists, similar to the one above, that computes co-moment. The apparent asymmetry in that last equation is due to the fact that, so both update terms are equal to. Even greater accuracy can be achieved by first computing the means, then using the stable one-pass algorithm on the residuals. Thus we can compute the covariance as. Likewise, there is a formula for combining the covariances of two sets that can be used to parallelize the computation. See also, algebraic formula for the variance, references, A.B. Boolean-Arson. Accuracy and reliability in scientific computing. Siam. PA 47. ISBN A978-0-89871-584-2. Retrieved February 17, 2013. ABTF Chan, G.H. Golub and R.J. Levesque. Algorithms for computing the sample variance, analysis and recommendations, The American Statistician, 37 ppA 242 Euro 247 Hyam, Nicholas. Accuracy and Stability of Numerical Algorithms. Siam A. A.B. Chan, Tony F. Golub, Jean H. Levesque, Randall J., Updating Formulae and a Pairwise Algorithm for Computing Sample Variances. Technical Report Stan CS 79-773, Department of Computer Science, Stanford University. Donald E. Muth. The Art of Computer Programming, Volume 2, Semi-Numerical Algorithms, 3rd ed., pages 232. Boston, Addison Wesley. B. P. Welford. Note on a method for calculating corrected sums of squares and products. Technometrics 4, 3, 419 Euro 420. Chan, Tony F. Golub, Jean H. Levesque, Randall J. Algorithms for Computing the Sample Variance, Analysis and Recommendations. The American Statistician 37, 242-247 http, www.jsto.org 2683386, link, Robert F. Comparison of several algorithms for computing sample means and variances. Journal of the American Statistical Association, Volume 69, Number 348, 859-866 doi, 10.2307/2286154, http, www.jahandcook.com/ standard_deviation.html, DHD West. Communications of the ACM, 22, 9, 532-535, Updating Mean and Variance Estimates, an Improved Method, Turriberry, Timothy B., Computing Higher-Order Moments on Linear, Par Copyright Bay, Philippe, Formulas for Robust, 1-pass parallel computation of covariances and arbitrary order statistical moments, Technical Report SAND 2008-6212, Sandia National Laboratories, A.B. Choi, Nguyen Khian. Sweetman, Bert, Efficient Calculation of Statistical Moments for Structural Health Monitoring. External links, Wellstein, Eric W., Sample Variance Computation, MathWorld.